representing complex numbers on the Argand diagram, so geometrical representation, the pictures of it. And as we've seen, we can represent our complex numbers as vectors rather than a point. And we've also seen the advantage of that. So here's our complex number x plus iy, which I'm saying we're going to represent with this particular vector. And the advantage with vectors is we can move them and they stay exactly the same. Unlike the point, as soon as you move the point, it changes when you move it somewhere else. So that vector I could slide down there. It still represents the same complex number. Head minus tail, whatever that is, that's the complex number it represents. I can put it up there. Again, head minus tail, still the same complex number. It doesn't matter where we put it, that length is going to stay the same, the direction is going to stay the same. It's a vector. Head minus tail. So adding and subtracting. Well, we've seen how we add and subtract vectors, so this will be exactly the same. If I've got this complex number, it's represented at that point, Z1, there's its vector. And if I want to add the point Z2, I slide the vector along, add them head to tail, that new point is the answer to Z1 plus Z2, wherever that vector ends up. And again, it doesn't matter which order you do it in. You go Z1 plus Z2 or Z2 plus Z1. And reminder with vectors, if we want to subtract, and instead of placing them head to tail, we place them head to head or add the negative vector. If I want Z1 minus Z2, then I add negative Z2 and I'm down there. There's my new one. That vector we can slide, and as we saw, it becomes the other diagonal of that parallelogram, head minus tail. This brings up this thing called the triangular inequality. It's a very simple thing. In any triangle, then one side will always be shorter than the sum of the other two sides. And that's simply because the distance between 2 points is always a straight line. That creates this. I know that the modulus of Z1 plus Z2, therefore, must always be less than or equal to the modulus of Z1 plus the modulus of Z2. We're talking about three sides in a triangle. It's formed by those vectors. It's also true with the difference as well. I mean, you can play around with that and come up with all sorts of things. And you could then also show that the modulus of Z1 plus Z2 would be bigger than Z1 minus Z2. Of course, it'd be the absolute value of that because we want it to be a positive number. Now, equality, when are they equal? That's if all 3 points are on the same line. So then the length of the two vectors would add to be the same as the additional because they're all sitting on one line. Here's a very old example. 1995, we've got a complex plane there, another name for the Argand diagram. P and Q represents complex numbers Z and W. Thus, the length of PQ is head minus tail, Z minus W. And basically, they're saying show the triangle inequality or explain that. To show that, all right, I'll draw in PQ. I've created this triangle. I know the length of OP is the modulus of Z, the length of OQ, the modulus of W, and the length of PQ is the modulus of Z minus W. And I can simply say, well, using the triangular inequality, then that modulus must always be less than or equal to the sum of the other two. Struck the point R representing Z plus W. Well, if I add them together, I would end up there. What can be said about this quadrilateral? It's parallelogram, because we have vectors here. We know opposite sides are both equal and parallel. Now, they put a condition on it. If the modulus of Z minus W is equal to the modulus of Z plus W, what can be said about W divided by Z? So essentially they're saying those two diagonals are equal in length. So we have to think about it. A parallelogram where the diagonals are equal in length. So we know it's better than just a parallelogram. If those two are equal, then the shape must be a rectangle, because that would be the parallelogram where the diagonals are equal. What can be said about W divided by Z then? Well, that means the angle between the two vectors must be 90 degrees, or pi on 2. That would be the angle in the rectangle. Angle between the two vectors would be the difference in their directions, or the difference in their arguments. So the argument of W minus the argument of Z is pi on 2. Using our rules, that means the argument of W divided by Z is pi on 2. So we know we've got a complex number where its argument is pi on 2. it must be a purely imaginary number then. It would sit on the imaginary axis. Its argument would be pi on 2. So that's what could be said about w divided by z. Okay, multiplication. Now remember the modulus, we just multiply the two together, but when it came to the arguments, we add the arguments together for multiplication. And we can prove that. But if we multiply z1 by z2, basically we're talking rotation. Multiplication is rotation by the argument. Anti-clockwise, and the length would get stretched by whatever the length is. That's dilation, if you like. We're going to multiply z1 by cis theta. There's the picture there. Now, if we multiply, we'll also multiply the length by a factor of r. Now, note, this one's so important. If the argument is pi on 2, we know it's imaginary, but if in addition to that the modulus is 1, then we're talking simply that I, cos pi on 2 plus I sin pi on 2 is I. Now therefore I z1 will rotate that vector OA 90 degrees. Now if that theta there, and obviously it's not in our picture, if it was pi on 2, 90 degrees, we'd get that rotation. Remember that, it's a key fact. Multiplication by I is a rotation anti-clockwise by pi on 2. Always remember, I know I've said it a few times, but can't stress it enough. Head minus tail, whenever you want to work out the value of that vector, head minus tail will tell you which complex number it is. Look at this picture. That's a square, by the way. I forgot to mention it there, I think, but that's a square. How can I find all these points? All I know, D is 1, and A we're just calling omega. So what would these other ones be? Well, DC then, if I just said that's a square, must be the rotation of DA by 90 degrees, which is multiplication by I. So I know it'll be DA times I. Well, DC would be, I don't know C yet, but it would be C minus 1, head minus tail. That would be that vector. And DA, head minus tail, would be omega minus 1, and that's going to be times I. That allows me to come up with an expression for C. C must be that, 1 minus I plus I omega. Okay, that finds C. Let's find B. Well, to get to B, I can say, well, from the point A, I'm adding the vector DC. That's how I would get to B. Now, it looks like I'm adding the vector AB. Well, it is, but opposite sides are equal and what have you. It's the same vector. Why did I pick DC? Well, I already know D, and we've just worked out C, so it makes sense to use that vector. B is what I'm trying to find. I can't use the vector that I haven't got yet. So adding in what we know. A was the point omega. DC, head minus tail, C minus 1, which we've seen over there is omega minus 1 times I. There's an expression for B. So negative I plus 1 minus I times omega. But hang on, I could have found B another way. I could have said from the point C, I'm going to add the vector DA. Now C, well, that's the one we just said was 1 minus I plus I times omega, plus DA, which is omega minus 1, head minus tail. Playing around with that, we obviously get the same answer. There's different ways of getting the answer, depending on which vector I want to play with. Of course, there's yet another way I could find B. This one's more interesting. I could say it's the vector dB here would be head minus tail. Now, how do I get the vector dB? I rotate the vector AD, but I'd only be rotating at 45 degrees, because diagonals in a square. But its length now is going to dilate. And we know that in any 45 degree triangle, right angle triangle, the sides are in the ratio 1, 1, root 2. That's how we got our exact value of sine and cos being 1 on root 2, things like that. So I must have multiplied the length of this vector by the square root of 2. That's why the square root of 2 is in there. So root 2 cis pi on 4 times the vector dA. Well, cis, that's cos plus I sine. Cos 45 plus I sine 45 times that by d minus a, head minus tail, omega minus 1. As I just said, cos of 45 is 1 on root 2, cancels with the root 2, so that's just 1. So it's 1 plus I. Expanding all that out, collecting like terms, and yet again we come up with the same answer. Probably not the easiest way of all three, but just show you that there are other ways of finding the point. Just play with vectors to try and get there. This one comes from the 2000 HSC. We're told OABC is a rectangle and OC is twice the length of OA, and this time A again, they've just called it omega. So what would C be? What's the complex number over there? Yeah, same sort of idea. How do I get there? How can I get from O to C, the vector OC? Well, I could have got that vector OA, rotated it 90 degrees, because that's the angle in the rectangle, but this time we've dilated its length by 2. So I'd multiply by 2i. All right? C then is just simply 2i omega. Because they're joined to O, we're talking about a position vector, not a displacement vector. So head minus tail will always just be the head in that situation. So now OC is just the point C, OA is omega, of course, there is OA. What complex number corresponds to the point of intersection D of the diagonals OB and AC? Well, we know diagonals bisect in a rectangle. It's something we know. But what it's really saying is, what's the midpoint of AC? Or what's the midpoint of OB? It doesn't really matter which one we pick. Now, AC is more sensible because I don't know what B is yet. So how do I find the midpoint when I don't know what one of the points is? It makes more sense to find the midpoint of AC. All right? So it'd be the point A plus the point C divided by 2. That's our midpoint formula. So subbing in what we know, A is omega, C we just worked out was 2i omega, that divided by 2, there's our point. Did I factorise? Yeah. So I factorised it and said, oh, well, that's the same as a half plus I times omega. Let's get a more recent one then. What have they been asking? Here's last year's. Complex number Z satisfies this expression. The modulus of Z minus 4 on Z is equal to 2. They've given us a bit of a hint. Use the triangle inequality, or otherwise, if you really want to go a different way, show that the modulus of Z is less than or equal to the square root of 5 plus 1. Okay. So OZ, I'll just draw a vector up there. There it is, OZ. And O4 on Z. I've made them position vectors, so I know the head is simply going to be those complex numbers, Z and 4 on Z. Okay, using the triangle inequality, okay, let's put in the third side. I've got a triangle. What would that triangle be? Head minus tail, Z minus 4 on Z, which is the one we're looking for. Okay, well now I can use my triangle inequality and say, well, by that, I know. I'm going to say the modulus of Z is less than or equal to, because that's what we're looking for in the question. It makes sense. So I'm saying that side will always be less than the sum of the other two sides. Now the modulus of Z minus 4 on Z plus the modulus of 4 on Z. Seems like a good place to start. But I got a value for that, because they told me the modulus of Z minus 4 on Z is 2. Don't know what the modulus of 4 on Z is, but I do know the modulus of 4 is 4. It's 4 over the modulus of Z. Hang on. Mod Z, that's what we're trying to find. I'll multiply everything by mod Z. Now I know mod Z is a positive number, it's absolute value. So the inequality sign won't change. I can multiply by mod Z, not an issue. I also know it's not going to be equal to 0 because it's on the bottom of the fraction. So modulus of Z squared will be less than or equal to 2 mod Z plus 4. Pull everything to one side. We've got a quadratic inequality to solve. I'm going to do it by completing the square. So the modulus of Z minus 1 squared is less than or equal to 5. Therefore, it must be in between negative root 5 and root 5. Add 1 to both sides, and you can see it drops out nicely. On the right-hand side, I get that 1 plus root 5. I don't really care about the left-hand side, because it's simply saying show that it's less than this amount. Well, I've done that. Sure, it'll stop at some point, but we're just interested in it's less than that amount. So it is true to say that the modulus of Z is always going to be less than or equal to 1 plus root 5. There was another question in last year's paper which was a little bit more interesting. You'll notice that one was question 15. It was still the second last question in the paper. This one was question 16. The last question in the paper, first part of the last question. They had this square in the Argand diagram, and they've given us the value of 4 of the vertices. Now, we know the complex number ZA, which is 5 plus I, ZB and ZC, we don't know what they are, but they lie on the square. But that triangle is an equilateral triangle. We have to find the exact value of that complex number ZB. That's all. We've got to put it all together. There's no parts to this one. It's one of these ones where it's not scaffolded for you. You've got to throw down all your ideas and hopefully we'll get some marks for it. Well, it seems to make sense to work out some values. Now ZB, notice that the imaginary part of the square is the same on that side. So I do know the imaginary part of ZB. It's also got to be 5i. It lies on that line. I don't know the real part though, so I'll just call it B, makes sense, it's ZB. I'll call it B plus 5i. I can do the same with ZC, it's lying on that horizontal where the imaginary part is minus 5i. Okay, vector U, I'm just going to call it U, head minus tail. ZB minus ZA. ZA I know at least. So that vector, which I'm calling U, will be B minus 5 plus 4i. And I'll create another vector, ZC minus ZA, which I'll just call vector V, head minus tail. That'll be C minus 5 minus 6i. Okay. But V is a rotation, it's an equilateral triangle, of 60 degrees, or in radians, pi on 3. So therefore V must be the cos of pi on 3 plus I sine pi on 3 times the vector U. Let's sub in all the things we know. We said V was C minus 5 minus 6i. The cis pi on 3, I know it's a half plus root 3 on 2i. And U is B minus 5 plus 4i. Expand that right-hand side out. Okay, so I've got a half times B minus 5 first. Outside would give me a half times 4i, well that's 2i. Inside, so root 3 on 2 times B minus 5. And last, that'll be root 3 on 2 times 4 I squared, which makes it a negative. So I get minus 2 root 3. Whew, remember, we're trying to work out what B is. It's only B I want to find. I don't care about C. So if I equate the imaginary parts, the real part must equal the real part, the imaginary part must equal the imaginary part, then negative 6 must equal 2 plus root 3 on 2 B minus 5. So I don't need to know point C. It was only in the real part, and I'm not using that. I'm just using the imaginary part here. I should be able to make B the subject of this. And there it is. Well, people probably were expecting a nice neat number, and it's not. There's no reason why it has to be. B is 5 minus 16 on root 3. I haven't bothered to rationalise the denominator, you'll notice. So therefore I now know ZB. It's that plus 5i, because its imaginary part was 5i. And there's the answer to that particular question. Okay, now 1e, let us play